So we are in 4.2. Let's continue. Let's look at a couple theorems. Theorem 1 states for constants, so for A, B, C, T naught, capital Y naught, and Y1 in R, so those are just real numbers, A non-zero, there exists a unique solution. So I don't know if you've seen that before, but when you do that, that means exists unique. So that if you go like this, backwards E and then exclamation, exists a unique solution. Okay, so there exists a unique solution to the differential equation ay double prime plus by prime plus cy equal to 0, with the initial conditions y of t naught is y naught, y prime of t naught is y1, and those are capitals right there. This y1 and those are capitals. Okay, so that the existence of a solution is kind of implied because we just found one. So, but it, is it true for all? And we kind of just developed some of that. So when I'm not going to get into theorem 1 in their book, in this book, they have the proof apparently in the expanded book, chapter 13. You'll see ours does not have chapter 13. So we're not going to do the proof of this one. So the existence part we're kind of constructing as we go, that it exists. And then we'll have other things to look at, basically. Let's look at the next definition. Definition 1. Two functions. Oops. Let's try that again. This is talking about linearly independent and dependent functions. We've already talked about that a little bit. This states two functions, y1 of t and y2 of t, are what we call linearly independent or we'll just abbreviate LI. So linearly independent on an interval, subset of the reals, so some I is an interval, if and only if neither of them are constant multiples of the other on all of I. So neither of them are constant multiples of the other on all of I. On all of I. So what that implies in that definition is if you can find one value or one point in I that they are constant multiples, then they're not linearly independent. All it takes is one value. So repeat that. We say y1 and y2 are linearly dependent on I if that statement's not true, essentially. So that's the dependence case. So we say the functions y1 and y2 are linearly dependent on I. Basically, so if otherwise. I didn't write all that out again because you don't really have to. And then we abbreviate that LD. So basically, there exists, there exists a value. I don't know what we'll call it. T naught, I guess I'll do. So if there exists a T naught in I such that y1 of t naught equals a constant k times y2 of t naught, that would imply linearly dependence. All it takes is one value in that interval such that you can show a constant multiple. Okay, that's going to come in when we do some of our proofs concepts here shortly. Okay. So one of the things we're doing often, and hopefully you saw this in Calc 3, I know you have if you took my course, we have to state like what these values or variables are. Like where are they? Like what is I? I is a subset of R. What is K? Well, K is a real number. Back here we defined what y1 and y2 were. They're functions of the variable t, because you say of t. Later on, we don't have to put it in because we already defined that they're functions. So I don't have to put in the of t. You can, it's fine. Okay, so those a lot of little things like that make this, next level stuff. Okay, now let's go on to theorem 2. Let's see if I can fit it in there. All right, so let's go ahead and I'll just copy that theorem over. And then we'll look at the proof of that. So here's the theorem. I already defined uniqueness or existence of a unique value. I don't need that little symbol in there. Okay, so here's the theorem. And I'll read it word for word and go over it. So if y1 of t and y2 of t are any two solutions to this system, or not system, I'm sorry, to this equation, a y double prime plus b y prime plus c y equal to 0. That's my second order linear differential equation with constant coefficients, and it's homogeneous, set equal to 0. Okay, so these guys are linearly independent on R. Then there exists unique constants C1 and C2. And actually, I guess I needed that. Then there exists unique. Oh, I already wrote that down. Sorry. I just didn't write it out. Then, so basically, this statement right here, then unique constants. So that's exist. That's where you can just, instead of writing all those words, you could just say there exists unique C1, C2 such that, and you say where they are in R. Okay, anyway. Moving along. Such that, and here's your solution. So that this sum of those two is a solution that satisfies the initial value problem. So that solution is satisfied by the initial value problem given back up here. Okay, so before we actually do the proof of that for theorem 2, let's look at another definition we're going to use. This is the definition, so we're going to need the definition of what's called a Wronskian. Okay, so this Wronskian looks like this. So Wronskian, you state, so I'm using different symbols than they do. I'm just going to define it, and then that's what we'll use. So let F and G be differentiable functions. We'll just say differentiable. Okay, then the Wronskian, so you say W, and then you usually use a bracket, of FG, and you can say of, let's just say X in our case, make it look familiar. is equal to the determinant of, so if you haven't done, we did this already, I think. So the determinant of, and you say f of x, g of x, and then f prime of x, g prime of x. And that's equal to f of x times g prime of x, and then you would say minus f prime of x times g of x. So you do, this is really the same idea. Like you do that product minus this product. So that product and then minus that. So that's how you define a Wronskian. You can do higher order Wronskians and do the same format where you'll have f prime, g prime, h prime, and then f double prime, g double prime, h double prime, and you still do the same derivative. Okay, so that we're going to use that concept because this lemma, we're going to use lemma 1 for the proof of theorem 2. Okay, and this one, I'm just going to state this, and we're going to use lemma 1 to prove theorem 2. So this one, I'm not going to prove it. It's in the book. So lemma 1 says, let A, B, and C be real and A non-zero. Okay, if y1 of t and y2 of t are any two solutions to our equation, so are any two solutions to our second order linear differential equation, the constant coefficient, ay double prime plus by prime plus cy equal to 0 on R. And if the Wronskian of y1, y2, and I'll say of z equals 0, I think they use tau right there, but it doesn't matter. Of z equals 0 for all z in R, then y1 and y2 are linearly dependent on R. So the contrapositive of that, so this is basically the implication is Wronskian 0 implies, so there's solutions to the equation. Okay, fine. If the Wronskian 0, then y1 and y2 are linearly dependent. The contrapositive of that says that's P implies Q. So not Q implies not P would be y1 and y2 are linearly independent, implies the Wronskian is not equal to 0. So keep that in mind. Okay. We'll look at that theorem or later. Or I'm sorry, you'll look at it later if you want. So the proof of that is page 161. And for lemmas, I wanted to mention the work, like the heavy lifting stuff, what takes a lot of work, is done in the lemmas. Is often the case. It's like they don't mean much as they sit because the theorem itself is more powerful, but often to break up the complexity of the theorem, you develop the limits, right? It's always axiom, definition, And then it's usually lemmas, theorems, lemmas and proofs, theorems and proofs, and then corollaries are results of those big theorems. So that's usually the order we go. Okay, so let's look at, so the one we're going to use lemma 1 and look at the proof of theorem 2. That's all we're going to really look at today. Or today, whenever you see this. All right, so write down proof of theorem 2. Okay, so we already know that it's assumed this, so I'll say it like this. So we already know that y of t equal to c1 y1 of t plus c2 y2 of t is a solution to I'll just do star. So to this above. So it's already, we'll just do it like that. Okay, so, I totally forgot to go back. Let's go back to theorem 2. So theorem 2 says, this is what we're trying to prove. y1 and y2 are any two solutions to that. Okay, fine. They're linearly independent, then unique constants exist such that blah, 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 blah. All right, so what we're trying to show is uniqueness. Okay, or that, not uniqueness. We're trying to show C1 and C2 exist. Okay, so what we get is we get the assumption that this is a solution. So, excuse me. Okay, so we know that is a solution. So we must show that we can find C1 and C2 so that y of t naught equals C1 y1 t naught plus C2 y2 t naught equals y naught. And similarly, y prime of t naught equals C1 y1 prime t naught plus C2 y2 prime t naught equals capital Y1. So basically what we're going to say is, if you go back up to the theorem, so we are assuming that y1 and y2 are linearly independent on R. So if they're linearly independent on R, then what do we know about the Wronskian? That's really the key there. Let's think about that. Okay, so the Wronskian, so if they're linearly independent, then the Wronskian is non-zero. So it goes back to this. Okay, so check this out. This system can be solved. So we're basically looking at just this linear system right here. So you can just use algebraic techniques to solve for C1 and C2. What you end up getting then is a denominator that's the Wronskian. So basically, I'm not going to write all this detail out because you can look at it kind of nicely. So I'm just going to say this system can be solved, like always, for C1 and C2, where the denominator of C1 and C2 is the Wronskian of y1, y2 of t, and it's non-zero. Since it is assumed that y1 and y2 are linearly independent, okay, so that's what's not, I think, clear at all in the book. You have this lemma that says if the Wronskian is 0, then y1 and y2 are linearly dependent. The contrapositive of that is if y1 and y2 are linearly independent, meaning not linearly dependent, then it's the negation of w equals 0. So then the Wronskian of y1, y2 cannot equal 0. Okay, so that's really the key. Okay, so I'll just write that down here just for maybe, hopefully, maybe a little more clarity. I'll say by the contrapositive of lemma 1, which is, of course, logically equivalent. You don't have to say that, but that's not as clear. Okay. So that's a little bit of, conceptual stuff, how to get these things, why they work. Let's go on to talking about distinct real roots and then repeated roots. And then we will go on to 4.3. So we have a little bit more to do in 4.2, at least one more video.